8 great ideas in computer architecture. Number 1, design for Moore's law. Number 2, use abstraction to simplify design. Number 3, make the common case fast. Number 4, performance via parallelism. Number 5, performance via pipelining. Number 6, performance via prediction. Number 7, hierarchy of memories. And number 8, dependability via redundancy. Design for Moore's law. The one constant for computer designers is rapid change, which is driven largely by Moore's law. It states that integrated circuit resources double every 18 to 24 months. Moore's law resulted from a 1965 prediction of such growth in IC capacity made by Gordon Moore, one of the founders of Intel. As computer designs can take years, the resources available per chip can easily double or quadruple between the start and finish of the project. Like a skid shooter, computer architects must anticipate where the technology will be when the design finishes rather than design for where it starts. Number 2, use abstraction to simplify design. Both computer architects and programmers had to invent techniques to make themselves more productive. For otherwise design, time would lengthen as dramatically as resources grew by Moore's law. A major productivity technique for hardware and software is used to abstraction to represent the design at different levels of representation. Lower level details are hidden to offer a simpler model at higher levels. Number 3, make the common case fast. Making the common case fast will tend to enhance performance better than optimizing the rare case. Ironically, the common case is often simpler than the rare case and hence is often easier to enhance. This common sense advice implies that you know what the common case is, which is only possible with careful experimentation and measurement. Number 4, performance via parallelism. Since the dawn of computing, computer architects have offered designs that get more performance by performing operations in parallel. Number 5, performance via pipeline. A particular pattern of parallelism is so prevalent in computer architecture that it merits its own name, pipelining. For example, before fire engines, a bucket brigade would respond to a fire, which many cowboy movies show in response to a dastardly act by the villain. The townsfolk form a human chain to carry a water source to fire, as they could much more quickly move buckets up the chain instead of individuals running back and forth. Number 6, performance via prediction. Following the saying that it can be better to ask for forgiveness than to ask for permission, the next great idea is prediction. In some cases, it can be faster on average to guess and start working rather than wait until you know for sure, assuming that the mechanism to recover from a misprediction is not too expensive and your prediction is relatively accurate. Number 7, hierarchy of memories. Programmers want memory to be fast, large, and cheap. As memory speed often shapes performance, capacity limits the size of problems that can be solved, and the cost of memory today is often the majority of computer cost. Architects have found that they can address these conflicting demands with a hierarchy of memories, with the fastest, smallest, and most expensive memory per bit at the top of the hierarchy, and the slowest, largest, and cheapest per bit at the bottom. Cache gave the programmer the illusion that main memory is nearly as fast as the top of the hierarchy and nearly as big and cheap as the bottom of the hierarchy. Number 8, dependability via redundancy. Computers not only need to be fast, they need to be dependable. Since any physical device can fail, we make systems dependable by including redundant components that can take over when a failure occurs and to help detect failures.